Okay, the next thing we need to do is assess how our model performed and make sure everything went as we'd hoped. So the first thing we can do is just use the print and then print our model here and look at the R hat and effective sample sizes. So here we can see all of our R hat values are 1, which is exactly what we want. So that looks good. And our effective sample sizes are all very high, right? So we have, out of a total of 24,000 steps, most of them are right around there. So this is great. Again, as long as these are over about 1,000, you should be fine. And so we're in very good shape. So it looks like our chains are mixing well and that they're not, each steps are not very correlated. And then, of course, we want to look at our trace plots. So again, we can use the stan_trace function to do that. And we can include the warm-up so we can see that this case is, it only takes a few steps in this model for our chain to actually find the peak and stay there. And all 3 of our chains are have found the same peaks for all 3 of the parameters that we're estimating. So that all looks very good. So it looks like our model performed as we expected it to. So for our next step, we can tentatively interpret our results. We can do this a few ways. So of course, we can just view the stats here. I find these tables not super intuitive to look at, though. I find it much easier to plot, to understand things when we plot things. So, but here our beta 0, the mean is 0, and the 95% highest density interval goes from negative 0.16 to positive 0.16, so clearly centered around 0. That makes sense, right? We standardize the data to be centered around 0. Our estimate for beta 1, so again, this is the relationship between weight and height, is the mean is 0.57 with a 95% highest density interval going from 0.4 to 0.73. So it's fairly wide, and so on. Anyway, you can see this. So again, I find this not super intuitive to see it in tables, but it is a good starting point. We've often looked at this anyway to look at our R hat values. So since the data is there, we may as well take a peek and see what it says. And we can also plot these estimates with the stan_plot function. So same idea, our beta 0 is centered around 0. Our beta 1 is kind of around 0.5, 0.6. And then our sigma estimate is just a little over 0.8. So that's fine and good. We can also get the data out of the stan format and plot it using our own functions, so using base R or using ggplot2. So we'll use base R, so we can extract the data as a data frame and just take a look at it to make sure it looks like how we'd expect. So again, we can use the as.data.frame function to convert our stan model into a data frame that we're going to call posteriors. And then we can use the head function to take a look at that and just make sure it looks like how we expect. So here we have 1 row for each step in the Markov chain, 1 column for our beta 0 estimates, 1 column for our beta 1 estimates, and so on. So this looks good. You can leave the data all together like that. It's up to you. I find it a little easier to separate them out, and then I really know what I'm dealing with. So I'm going to make a new vector called ZB0 because this is our standardized coefficient for beta 0. And so I'm just going to assign to that our beta 0 values from our posteriors data frame. And then the same thing for beta 1 and sigma. Again, because these are our standardized estimates, I'm just sticking a Z in front of it. And so we can interpret these directly. So again, often with regression, we're not super interested in the beta 0 parameter. Like usually that's just there. We need that there for the model to function. And often we're just interested in this beta 1 estimate. Not just, but often this is our main interest. And so if we look at the mean value here, so it's about 0.57. And since the way that we've standardized the data, this is called a Z transformation, which is actually why I've put a Z out in front. So when you take a value, subtract the mean, and divide by the standard deviation, that's called the Z transformation. When you have the data transformed like this, it actually is quite meaningful. So they talk about this in the paper that I've assigned to you. And so how this can be interpreted is that a change in one standard deviation in height results in a change of 0.57 standard deviations in weight, right? So that's what this means. And you can actually do the math and convert this back, right? So we know the standard deviation in height, and we know the standard deviation in weight in the raw values because we calculated those at the beginning. And you can see that this would work out to the same estimate as what we got with the frequentist approach. But what's nice about this is universal, right? So if you're trying to compare regression results across studies or across types of analyses or types of predictor variables, they're all going to be on different scales, so it'll be hard to compare them. But when you standardize them all, then they're all relative to the standard deviation in the predicted variable. And you can compare that across studies and across parameters. So for most of the course, we're actually just going to interpret the standardized values. But I know it takes a while to get used to that. So what we can do is convert them back to the original scale. And I'll show you how to do that. So for our regression coefficients, other than the intercept, you can always use this equation to convert them back to the original scale. So it's the standardized coefficient times the standard deviation in our y variable divided by the standard deviation in our x variable. So this will always work across our regressions. It's always going to stay the same. So that is how we convert our beta 1 coefficient back to the original scale. And so we can do that. Then we can use these functions we've used before. So we can calculate the mean of this coefficient in the low and high 95% highest density intervals. And then we can plot them. So here we're plotting a histogram of our beta 1. I'm just changing the color here. And I have, if you want to use Greek symbols in R, you can use this bquote command. And so this is going to give me a Greek beta with the subscript 1, because this is our beta 1 coefficient. And then we have, so I'm going to plot a histogram of these beta 1 values with a point at the mean, and then the line segment showing the boundaries of the low and high 95% highest density intervals. So we've done this before. So none of this is new. What is new is I've added some commands for adding the mean and the highest density values to the plot. And you don't need to know this. This isn't crucial for this course, but so I'm not going to walk through how to do this, but you're welcome to dive in, right? And so it's this mtext command, and so you can just look up the help for that. And then also this paste command is what allows you to combine text with actual values that are from your data. So if you're welcome to look into those two commands, mtext and paste, and you can understand why this command does what it does. So this is the result from that. So we have a histogram of our beta 1 estimates. This is our effect of height on weight. And then this is plotting the mean value and the segments outlining the highest density interval. And then here I just have it plot the text. So the mean value and then the boundaries for the highest density interval. So we can also convert sigma back to the original scale, and this equation is always going to be the same no matter what regression we're doing. So the sigma back at the original scale is the standardized sigma times the standard deviation of y. And then the rest of this is the same as what we just did. So then we're calculating the mean, low, and high 95% highest density interval, plotting a histogram, and adding those values. So here we get that information for sigma, and here we've got the Greek sigma here as our x label using the bquote function. And then we can also convert our beta 0 back to the original scale if we want to. This equation is a bit more complicated. So it's always going to have this component. So the standardized beta 0 times the standard deviation of y plus the mean of y. And then you subtract this information for each of our parameters. So we have z beta 1 times the standard deviation of y times the mean of x divided by the standard deviation of x. Of course, if we had two x values, it'd be zb2, so minus zb2 times ysd times, anyway, we'll get into that. We'll do this later. But this gets a little more complicated, but that's okay because often we're not super interested in it. So we can often not need to convert this back to the original scale, but we'll go through it a few times. And then this is all the same as before, calculating the mean, the low, the high, and plotting it. And so we can see that here. You can see these values are very similar to what we got using the frequentist approach. Okay, the next thing we need to do is to conduct posterior predictive checks. And so here I say evaluating the signal and the noise, because we're going to do this two different ways. There's two ways that we can do this. So again, the whole point of a posterior predictive check is to use our estimates for the intercept and the slope and our x values to calculate what we expect the mean value to be for each y value and compare our expected to the observed values. And so, yeah, that's kind of, we're getting this to the signal and the noise. And this is actually the name of a book by Nate Silver. I don't know if you have heard of him. He has the website 538. He's kind of the most famous Bayesian statistician. He accurately predicted, I think, every state in the second Barack Obama election. And so he became kind of famous for that. And so the news site 538 applies Bayesian statistics to all sorts of daily activities. Anyway, so we can do posterior predictive checks, again, two ways. One is just looking at the deterministic component of our model. And then again, we can look at it adding that unexplained variation to the model as well. And you'll see how we do that. We'll walk through both ways. So this deterministic component, so we can assess the fit and uncertainty in our estimates of the mean weights across the range of height values. So what we do here is for each step in the chain, we use the posterior values of beta 0 and beta 1 in combination with the height data to predict weight. Okay, so how are we going to do this? We did this before with our other model, but now we have more parameters, so it's a bit more complicated. So first I'm just going to get the length of our chains, and I'm going to call that chain length, and it could be the length of any of our parameters. They'd all be the same length. But now I'm going to make a new matrix for holding our posterior predictive values. And so this is going to be a matrix that is going to fill with NAs, and each row is going to represent a step in the chain, and each individual is going to have its own column. So for each individual, we're going to have 24,000 predicted weights based on their heights and our estimates of beta 0 and beta 1 for that step, for each step in the chain. So we're creating this matrix. And so we can do this with the calculation with a few loops. So we need to step through every step in the chain. So for I in 1 to chain length. Then for each step in the chain, go through each individual. So for j, so a new variable for j in 1 to n, then we predict a new weight for that individual based on the values for the intercept and slope for that step in the chain. So in our ith row and jth columns, again, the rows refer to the steps in the chain, and the j refers to the columns, which is the individuals. So for each row and column is going to equal the intercept value for that step in the chain plus the slope value for that step in the chain times the height of that individual. Okay, and so this is what this is going to do, is calculate the predicted weight for each individual in each step of the chain. So this is going to be a big matrix, right? Now we want to do the same things as before. We want to get the mean predicted weight for each individual and the high and low highest density interval. And again, you could do any interval you want. I'm just doing the 95% interval just because. But now we can't just do mean, low, and high, because we want to do this across all individuals. And we don't want to kind of do it separately for each one. So what we can do in R is there's this handy function called apply that allows you to apply a function across a data frame or a matrix, and you can do it by rows or columns. So this is how this works. So we're going to use this apply function. The first argument in this function is the data frame or matrix across which you want to apply a function. Then the second argument is an indicator of whether to apply the function to rows or columns of the data. So we want to take the mean, we want to get the mean and the low and high for the highest density interval for each individual. And remember, the individuals are different columns. And so we want to apply this function across columns. And the function that we want to apply is the mean. So what this is going to do is apply the function mean across the columns of this matrix. And so we do that for the mean and to calculate the low quantile, the upper quantile, and then we're putting them together into a data frame because we're going to plot this in ggplot2. And so here we're storing the mean, the low and the high cutoff value for each individual, as well as the original x and y values, because we want to plot these too. Then in ggplot, we're going to tell it what data frame we're using, change the theme. Then I'm going to add points for the original values, so our original x and y values, and we're going to make that transparent. And then we're going to plot the mean predicted values. So our x values are still going to be our original x values, but now our y values, instead of being the observed y values, these are going to be our predicted mean values. I'm going to make these a different color, so they're going to be blue, and they're also going to be transparent. But now to show the low and high highest density interval for each individual, I'm going to use what's called a ribbon plot, so geom_ribbon. And for this, you give it x values, so these x values stay the same, and then the minimum and the maximum y value for each x value. So our y minimum values are our pred1 low, so our lowest cutoff for the 95% highest density interval. And our y max is our pred1 high. And then I'm going to fill this ribbon with a different color and make it transparent, and then just add some labels. So if we do that, it looks like this. So the estimates of our deterministic part of our model look pretty tight, right? So our estimates of the mean weight for people of each height, it's pretty tight. But it's clearly that we're missing some key parameters in our model, because look at all this unexplained variation, right? So a lot of unexplained variation in weight exists, which is shocking, I know, right? Okay, so now let's do this a different way. So now we can do it with the full model. So if we've done our model well, then our 95% highest density interval should capture 95% of all the data points. And our full model should consider both the signal and the noise, right? So this was the signal. So this is how much information in weight are we getting from height. But now we're going to include that, but also add all the unexplained variance, which was included in our sigma parameter in our model. So this is all going to be very much the same. So now I'm going to make a new matrix called postpred2, but it's going to have the same values, right? So it's going to be the same size. It's going to have one row for each step of the Markov chain and one column for each individual. We're going to step through it the same, But now we need to add the extra variation. So this is just like our likelihood, right? So now our mean predicted value is exactly what we had before. It's the intercept for that step in the chain plus the slope for that step in the chain times the height of each individual. And that's going to be our mean predicted value. But the actual value that's going into each position in our matrix is going to be one random pull from a normal distribution with a mean of this and a standard deviation using our sigma from that step in the chain. Remember, we estimated this sigma for our data too. So this is the unexplained variance in our model. And so we're using the R norm, or randomly drawing from a normal distribution one value with these characteristics. And so that now we're including the noise, right? Our sigma value here. And then the rest of this is the same, right? So we're calculating the mean, the low and high, 95% highest density interval, making it into a data frame, and then plotting it in ggplot2. So if we do that, we get this plot. So you can see there's a huge amount of unexplained variance here, but it does capture 95% of the value. So this, it looks like our model is kind of doing what we expect it to. But this shows, or actually I think I have them side by side. So this makes it look like our model is pretty good, right? But when you account for the unexplained variance, we're very uncertain about someone's weight if we know their height. And this, including that sigma estimate, accounts for all that unexplained variance in our knowledge about the relationship between height and weight. Okay, we'll stop there for now.